Okay, good morning everyone. Welcome to the virtual field trip for the northwest of Scotland in the Assynt window. I'm Mike Searle.
I'm Richard Palin.
And we're going to present you with 4 video sessions across the field trip, exactly as if you were here in the field with us. You'll have to excuse us sometimes if we do this because it's midsummer and the midges are flying out and it's really quite difficult conditions, unlike when we're normally here in April when the sun's shining and Scotland is beautiful clear skies. Okay, welcome to the virtual Assynt Northwest Scotland field trip for 2020. I'm going to run through now exactly what we're going to do on the whole 4 or 5 video sessions of this field trip. But first of all, to put you in the picture of where we are, here is a map of Scotland, northern Scotland, and we are now in Inchnadamp in the middle of the Assynt window here. The Moine thrust zone, for which this area is world famous, runs from the north coast of Scotland at Loch Eriboll all the way down to the Isle of Skye. And this is the Caledonian mountain front, which divides the Laurentian plate margin to the west from the Avalonia plate to the southeast. So Laurentia is, when you close the Atlantic, Laurentia is part of the eastern seaboard of Canada, North America. It goes north as far as Svalbard and probably much more extensive. There is another plate, the Baltica plate, which is Scandinavia, and the southern plate here is called Avalonia. So it's a 3-way continental collision zone between Laurentia and Baltica and Avalonia. In Scotland, we're looking at the Laurentia Avalonia plate collision, and this is a 2 continental plate collision that closed the Iapetus Ocean in much the same way that the India-Asia collision created the Himalayas. So what we're going to look at here is both the fallen sequence of the Laurentian plate margin and the Moine thrust zone in particular, which is the world's classic fold thrust belt. So to run you through the stratigraphy, basically, we have 4 units on the foreland sequence, which are summarized in this stratigraphic diagram here. And we're starting off at the Lewisian basement. These are the Archean, oldest rocks in the UK, Archean granulite and amphibolite facies gneisses that form the basement, the lower crust. They are unconformably overlain by a thick sequence of Torridonian sandstones. These are unfossiliferous Proterozoic sedimentary rocks, Arcosic red beds, sandstones, conglomerates. Both of those units are unconformably overlain along a major unconformity by the Cambrian Quartzites. So this marks the establishment of the Cambrian Ordovician sedimentary sequence for the eastern margin of the Laurentian plate. And these comprise the lower Cambrian Quartzites, which are characterized by these large-scale cross-bedding. This upper unit here is called the pipe rock because they are characterized by worm burrows, trace fossils of worm burrows that we can see beautifully exposed in this upper section of pipe rock, overlain by a thin section of Fucoid beds, Fucoid grit. These are red siltstone sandstones deposited in a lagoonal type environment, overlain by a thin section of Salterella grit. This is a return to arenaceous quartz sandstones, and these units are all overlain by a thick sequence of limestones and dolomites. This is called the Durness group. They're dominantly lower and middle Ordovician, and this marks the establishment of a major shelf continental margin along the Laurentian plate. So this is the stratigraphy that is exposed along the foreland of Laurentia, and these rocks here are also all involved within the Moine thrust zone. This is the foreland. The hinterland is composed of central and eastern Scotland. This is all the metamorphic rocks of the Moine supergroup. These are Arcosic, Samitic, and occasionally Peolitic meta-sedimentary rocks dominantly, also overlying little inliers of Lewisian basement. So the Moine thrust was initiated within the Lewisian continental crust. On day one, we're going to do an introduction to the stratigraphy of northwest Scotland. So we're going to be walking a section along the north shore of Loch Assynt and running through the entire stratigraphy from top to bottom. On video 2, day 2, we will concentrate on the Moine thrust zone tectonics. On video 3, we're going to concentrate on the Lewisian basement gneiss. And on day 4, we're going to go up to the north coast of Scotland to Durness, Sango Bay and Loch Erebol. And we're going to do a complete transect across the whole north coast of Scotland from the Lewisian foreland to the Moine, crossing the faults that can be connected to the offshore Scotland in the Devonian and extending across to the Moine thrust zone in Loch Erebol. So throughout this course, throughout all 4 or 5 videos in this session, you need to refer to the field guide. It's very important that you have the field guide handy when you are looking at the video, because we will continually be referring to diagrams, for example, like this, which is the compilation of the stratigraphy of northwest Scotland. This is the very first map that was produced by the Geological Survey of Great Britain, Peach and Horn, in 1890. It was published in the Memoir of 1907, and it is a spectacularly good piece of work. It is almost faultless today, and the modern map, which is produced by the Geological Survey, is this one here. And this is the one we're going to continue to refer to throughout the course of this fieldwork. So to put you in the picture, this is the foreland over here in the west. The red is the Lewisian gneiss. The green and the purple are the ultramafic and mafic dikes, the scoury dikes, that intrude through the Scaurian Precambrian gneisses and are affected by the later Laxfordian deformation and metamorphism to the south and to the north. The Lewisian gneiss basement is overlain by the Torridonian Sandstones in orangey yellow. And these are the Proterozoic conglomerates, red beds and sandstones that form all the highest mountains of the Assynt Peak. So Sulven, Canisp, Quinag, Coolmore, Coolbeg, they are all made of Torridonian sandstone sitting unconformably on the Lewisian basement. Both Lewisian and Torridonian are overlain again unconformably by the Cambrian Quartzites, which is this grey unit here. So we have 2 unconformities between the Lewisian and the Torridonian, and between the Cambrian and both underlying units. And occasionally they meet at a double unconformity, which we will see shortly in the field right here on the south shore on the north and south shore of Loch Assynt. That's the foreland section, the undisturbed foreland section. And then we have the Moine thrust zone, which is this zone of complexity. You can see that there's numerous thrusts, this symbol here with the little ticks on, and it includes rocks, all of the rocks that we see in the foreland, including the Lewisian and the Torridonian, the Cambrian Quartzites, the Durness limestone. All of this is imbricated up in a series of spectacular folds and thrusts. There's several thrusts running through the middle of the Assynt window, and the 2 most, apart from the Searle thrust, which is the lowest and the youngest, we have the Glencoul thrust, which is exposed spectacularly in Loch Glencoul, which we'll also see later on today. And that brings up a sheet of Lewisian basement over the Cambro-Ordovician section. So you're putting older, deeper rocks over younger, shallower rocks. The Glencoul thrust is at a similar structural level to this thrust here, which is called the Benmore thrust. And that brings up again a slice of Lewisian basement together with Torridonian and Cambrian folded onto the Cambro-Ordovician section in the footwall. There's 2 major complications in the Assynt window, which are these 2 major intrusions. These are the Alkali igneous intrusions of Loch Ailsh and Borrolin. And these are incredibly useful rocks because they are syenitic rocks, cave feldspar rich granitic type rocks that were formed intraplate immediately prior to the thrusting.
And we know that because the Lochalge pluton is bounded at the top by the Moine thrust, and it's carried on the Benmore thrust below. The Borrolin is structurally lower, so the Benmore thrust truncates the top, and it's carried on a thrust that we call the Borrolin thrust that underlays this unit here with lateral ramps either side of it. We can date these rocks because they have zircons in, so uranium lead ages of these zircons, which are all done by the BGS, good enough et al., are around 431 to 429, the same age as the Canis porphyry, 430 on the foreland. So all of these alkaline igneous rocks were produced in a very short time interval immediately prior to the thrusting along the Moine thrust. In addition to the Canis porphyry, the Borrolin and Lochalge syenites, there is a whole unit of dikes. Now these are all of varying composition, from lamprifiers, which are mantle-derived mafic intrusions, up to peralkaline rhyolites, which have a chemical composition very similar to the syenites. And these are affected by the thrusting. So all of these igneous intrusions intruded through the foreland sequence, the Moine thrust zone, immediately prior to the thrusting, and they're affected by the thrusting. The uppermost thrust is this one here. This is the Moine thrust, which forms the oldest, the furthest travelled, and the first to move. And the Moine thrust carries the Moine schist, all this yellow material here, which extends right across to eastern Scotland. And these are metamorphosed metasedimentary rocks, metasamitic, arenaceous, and occasionally metapelitic, shaly rocks, that we can determine pressures and temperatures from and date using uranium-lead monazite ages. So this is the hinterland, which is the crustal thickening of the plate immediately after the two-plate collision. Okay, so that's an introduction to the tectonic setting of northwest Scotland in terms of the Laurentia-Avalonia plate collision and the Moine thrust zone. What we're going to do now is to go out into the field, and on day one we're going to walk a stratigraphic section along the north shore of Loch Assynt here, from the Lewisian basement to the Torridonian cover to the Cambro-Ordovician sedimentary section, and this is on the stable foreland. So we're going to start off in the basement, and we will end at the Searle thrust, which comes through right here, very close to Inchnadanf. Tomorrow, in the next video, we will concentrate on the thrust tectonics above that in the Moine thrust zone.
Okay, so we're going to do 4 video sessions on the whole of the Caledonian orogeny part of the Moine thrust zone in Scotland. And the first one we're going to do today is a transect across the foreland region here up to the Searle thrust, which is just at the end of Loch Assynt. The second one we're going to do is going to be concentrated on the Moine thrust zone, and this is one of the classic localities in the world where thrusting was first discovered more than 100 years ago in this very locality in the Highlands. The third one will be on the Lewisian basement gneisses. These are the granulite and the amphibolite facies gneisses that form the lower crust, and again they are the oldest rocks that we see in the UK, and we were going to have 2 sessions on that at Scowrie and Achmelvik. And the fourth one will be a transect across the whole of the Caledonian orogeny along the north coast of Scotland, from the foreland region at Cape Wrath to Durness to the Moine thrust at Loch Erriboll, and all the way across to the Moines itself. So that's the plan of campaign for the whole of this virtual field trip. To put us in the picture, what we're looking at on this field trip is the geology of northern Scotland, and this involves the Laurentian plate margin, the North American plate margin, which comprises the Lewisian basement, these rocks here in pink. These are outcropping in the Outer Hebrides in Lewis and Harris, and also along the west coast of Scotland up here. Those are the deepest, oldest rocks in the UK. They're about 2.7 billion year old gneisses, granulite facies, amphibolite facies gneisses, and they are unconformably overlain by a section of conglomerates and fluviatile sandstones and sedimentary rocks called the Torridon group, the Torridonian. Both of those units are cut along an unconformity and overlain by Cambrian and Ordovician sedimentary rocks that formed the passive margin of the Laurentian plate margin. Now, about 450 million years ago, the Laurentian margin collided with Avalonia, England, along a suture zone that occurs down here in southern Scotland, in the southern uplands and this region here. So Avalonia to the south, Laurentia, North American plate margin to the northwest, and we are concentrating along the Moine thrust zone, which is this zone of deep thrusting onto shallower levels, which occurs, outcrops from Loch Errobol in the north all the way down to the Isle of Skye in the south. And this is one of the classic locations in the world where thrusting was first discovered more than 100 years ago. This is the first geological stop on this field trip, and the point of this stop is to put you in the picture of the regional geology of the foreland region of northwest Scotland. So we're standing on the Laurentian margin, and the loch in front of us is Loch Assynt, and this is an east-west loch that goes from Inchnadanmph over there to Loch Inver in the west, and we're looking up at this mountain ahead of us here. And the most prominent thing we can see is this horizontal bedding in the rocks. You see the bedding in those are the red sandstones of the Torridonian conglomerates and fluviatile sandstones that sit unconformably on the Lewisian basement. So right above the loch you see hummocky ground with trees. That is the Lewisian gneiss basement. And there's a very prominent line which is the unconformity. It's an irregular margin like this. It has topography in it, on which the Torridonian sandstones are sitting on top of the Lewisian gneiss. A further complication on the left-hand side ridge over there is you can see from the summit there is another sedimentary unit. You can trace bedding dipping at about 20 degrees towards the east, which cuts out the Torridonian sandstones. Those are the Cambrian Quartzites, which is what we're standing on here. So we have two major unconformities in this region. One is the base of the Torridonian sandstones over Lewisian gneiss, and the other one is the unconformity that puts the Cambrian Quartzites on top of the Torridonian and the Lewisian. And where the two unconformities meet, this is the point, we call it the double unconformity. And you can see it in the landscape over there. If you trace the 20-degree dip of the Cambrian Quartzites down, it rests directly on the Lewisian gneiss, right over on the far side of Loch Assynt. And over here, all of the Torridonian section is cut out. So the Cambrian unconformity cuts both Lewisian basement and Torridonian in the foreland. In the very far east of Loch Assynt, the first of the thrusts come in, and if I draw this schematically here, this is the lowermost thrust of the Moine thrust zone. We call that the Searle thrust. We will look at a lot of this section in the thrusting sequence in the next video tomorrow, but today we're going to concentrate on these foreland units. So we're going to start off at the Lewisian basement, and we're going to work up stratigraphic section through the Torridonian, through the Cambrian Quartzites, to the pipe rock, to the Fucoid beds, to the Salterella grit, and finally to the Ordovician Durness limestone. So we're going to look at a succession of these stratigraphic units as we go up the stratigraphic table, from the Diabeg Formation at the base of the Torridonian to the Applecross Formation, which forms all the high mountains of Assynt. Sullivan, Canis, Quinyag, Stackpolly are all the Applecross Formation, red sandstones, conglomerates and arcosic sedimentary units. The major unconformity at the base of the Cambrian Quartzites is the base of the Cambrian basal quartzite succession, which is a thick unit of very pure orthoquartzite bearing rocks overlain by what we call the pipe rock, the upper unit of the Cambrian quartzite sequence, which we're going to see in a minute. That is overlain by the Fucoid beds, which is a thin, shaly unit, and the Salterella grit, which is a return to an arenaceous unit. So we're going from very shallow beach sands to a slightly lowering of sea level to a deepening event with the Fucoid beds back to a shallow succession in the Salterella grit. And the whole thing is overlain by the Ordovician Durness limestones, which form up to a kilometre thickness of limestones and dolomites in shallow water successions along the Laurentian plate margin.
So here we are at the first stop on the first day on the roadside, and we're going to be looking at the oldest and the deepest rocks in the succession. This is the Lewisian gneiss. So these are extremely old. They formed from magmas that were extracted from the mantle at about 3 billion years ago. And then they were subject to burial metamorphism, and they became high-grade crystalline metamorphic rocks with nice foliations. There's two particular rock types here. One of them is light-coloured. It's a felsic orthogneiss. And the other one is dark-coloured. It's a mafic orthogneiss. There's two types of gneiss in this outcrop. One is a light-coloured felsic orthogneiss. And the other one is a dark-coloured mafic orthogneiss. Now the one that's actually in the outcrop here is the felsic orthogneiss. And it's nicely banded. It has a foliation defined by dark-coloured orthopyroxene. And in between those folia, there's quartz and plagioclase feldspar. Now there's been some retrogression in these rocks, and the orthopyroxenes have been slightly degraded to hornblende and biotite, which are lower temperature minerals. But when the rocks actually formed, they would have been granulite facies, which is really quite hot and quite deep in the earth. These form parts of the lower crust of the mountain belts that we see today. These felsic gneisses are colloquially called grey gneisses, and they make up the bulk of Archean terrains all around the world. Now they're compositionally tonalites, trondhjemites, and granodiorites, so TTG gneisses. And they're very common. They're common of terrains this age, and they're thought to be remnants of Earth's first continents when they formed from differentiation of a more mafic protolith. Now this leads us on nicely to the mafic orthogneiss, which is further down this outcrop. So this is the second type of gneiss that we found in this outcrop. It's much darker than the previous version. It's one of the mafic gneisses, and it has a compositional equivalency to a basalt, but it's not an igneous rock, it's a metamorphic one. So these were originally mafic volcanic rocks that were buried to considerable depth in the early Earth, say 25-30 kilometers, and they were heated up and the pressure increased, and they transformed into a metamorphic gneiss again. Now in these rocks we can see plagioclase feldspar, clinopyroxene, and probably a bit of orthopyroxene. But again, these have been subject to a bit of retrograde metamorphism, just like the felsic version, so there will also be some hornblende and biotite in these rocks too.
So Richard is walking on the Lewisian outcrop, and above his head is the irregular unconformity that puts the flat-bedded Torridonian Sandstones above the Lewisian gneiss. And right up on the summit of Quignag, above it on the skyline, is the Cambrian Quartzite that cuts down on another unconformity, 20 degrees dipping to the east. So we have two unconformities in one view. Richard's feet are standing on the unconformity which puts Torridonian sandstones and conglomerates over the Lewisian gneiss, and if we pan up, the horizontal bedded Torridonian sediments are truncated themselves by the Cambrian dip of the Cambrian Quartzites, which is about 20 degrees to the east and is exposed on the summit ridge of Quignag. Okay, this is the unconformity at the base of the Torridonian succession, which overlies the Lewisian gneiss. And you can see the fabric in the Lewisian gneiss is at a very high angle to the flat-lying unconformity. So this is the unconformity with more than 1 billion years of time missing across it. The base of the Torridonian is defined by the Diabase formation, which forms a lot of these gully infills, woody conglomerates, red beds and paleosols. That is overlain with another unconformity by the Applecross formation, which forms all the big mountains in Assynt. Sulven, Canis, Quignag are all formed by the Applecross Formation, which is up to 2 kilometres thick, overlying the Unconformity. So we're actually on the Unconformity between the base of the Torridonian and the Lewisian on this diagram right here. Now, as we've seen before, the double Unconformity is where the base Cambrian Unconformity cuts across all the units beneath. So in some places the Cambrian Quartzite rests directly on the Lewisian basement. On some places there's 200 or 300 metres of conglomerates of the Torridonian succession between the Cambrian and the Lewisian.
So here we've come to the lowermost unit of the overlying Cambrian succession. This is a orthoquartzite. It's a quartz-rich rock that has a quartz cement. It's essentially monomineralic. And there are some red streaks inside which represent hematite alteration, oxidation of iron that may exist in the rock as well. Now this unit is very useful for telling us about the paleo-environmental deposition environment. So one can imagine some very tall mountain belts over in the west that were being eroded and weathered away by the wind, water and the ice. Now all these minerals are transported down topographic gradients and they're carried along in the river. Some of the hardest minerals, the most durable ones, such as quartz, will be transported the furthest. Some of the weaker minerals like mica and hornblende and feldspar will be broken down. So the end result is that you get a very pure quartz sandstone being deposited on these beaches. And we know that the rivers were flowing from what is now west to east by the direction of the crossbeds, because we can see this progradation, this growth of these layers heading off in that direction. So the very hard minerals are transported down the entire length of the river and they're deposited in this beach environment. Now the asymmetry in these crossbeds tells us about which way the rivers were flowing. So these inclined beds are prograding out in a particular direction that's in the direction of sediment transport. So we can infer from these orientations in the field that we had high mountains in the west and low-lying basins in the east, which the sediments were being drained into. In 3 dimensions, the Skelethos trace fossil is like a vertical tube. So on the surface of these bedding planes, we just see a circular impression. This is these white circles you can see, 1 centimetre wide perhaps. Now if we go to cross-section, looking down through the beds, we can see them as these vertical white burrows, maybe 2, 3, 4 centimetres in length. And this is the trace of where these worms were drilling into the soft sediments in this marine environment. So the next lithostratigraphic unit above the quartzite is the pipe rock. Now the pipe rock has its name from these vertical burrows that we see both in cross-section here and on profile on one of these exposed bedding planes. Now the pipes are trace fossils and they're remnants of worm-like animals that were burrowing into the rock on the very surface of the rock as it was in this kind of shallow marine beach type environment. And the worms would burrow down and bioturbate the sediments.
So the next stratigraphic unit above the pipe rock is this unit called the Fucoid beds, which is a wavy brown dolomitic siltstone, and you can see here it's full of burrows. It's very different from the last outcrop. It's a much more lagoonal facies. And you can see here that there are all sorts of contortions and layerings to it. A lot of these burrows are trace fossils again, which include things like worm burrows, similar to the last outcrop. But there's also a lot of other material in here, like echinoderm, sea urchin spines. There are Cruziana trace fossils in here, which are trilobite tracks. We don't see the actual fossils in the rock, but we do see evidence that the animal has been there. So some of these impressions here were originally thought to be fossil seaweed, which is why it was called the Fucoid beds. But we now know they're not seaweed at all. They're actually burrows from worms and animals that were living in this sort of muddy, silty backwater to the shelf sequence that we're looking at here.
The next unit up from the Fucoid beds is the Salterella grit. Now this is another quartz arenite, resembling the pipe rock that we saw earlier, but you can see that it lacks many of the Skelethos trace fossils that were exposed very nicely in the previous outcrops. This is a well-sorted, light-coloured sandstone, and it represents a shallowing of the sea level from the previous exposure, where the clay minerals were more easily dominated, more easily deposited. The name Salterella comes from very small fossils that exist in the rock, kind of shaped like ice cream cones. They're miniature mollusks. They're too small to see, unfortunately, but they make very dark spots in the rock all over. So the unit that lies directly above the Salterella grit is the Igneous limestone. Now this is a pale grey, subtidal, fine-grained limestone, and it contains many other fossils. And this transition here, this contact between the beds, marks a sea level rise. So it's the beginning of the deposition of rocks on a carbonate shelf. And these rocks become very thick elsewhere in Scotland, up to 2 kilometres thick, the limestones. The contact between the two units can be seen here. It's a fairly sharp transition between the rock types. And the Igneous limestone represents the establishment of a carbonate shelf on the passive margin of Laurentia, with the Iaptus Ocean off towards the east.
We spent the whole day walking through a section of the stratigraphy of northwest Scotland, starting off in the Lewisian basement, the basement gneisses, and we saw the unconformably overlying red beds, red sandstones and conglomerates of the Torridonian succession. And then there was a major unconformity cross-cutting both of those units, which was the establishment of the Cambro-Ordovician sedimentary sequence. The base of that was the cross-bedded sandstones and quartzites. Above that was the Skelethos worm tube arenites and quartz arenites, overlain by the Fucoid beds, the brown shaly siltstones, overlain by the grit with Salterella, the little tiny mollusks in. And then there was a major onlap with the establishment of the limestone shelf margin. This is the Igneous limestone sequence, which is a variable thickness and occurs throughout the Moine thrust zone. And the Igneous limestone is dominantly lower and middle Ordovician, and it marks the establishment of a major carbonate shelf along the passive margin of the Laurentian plate as the Iaptus Ocean was spreading. So having established the stratigraphy of northwest Scotland, looking at all the rocks here, there's another important aspect to this, which is the intrusion of igneous intrusions, dominantly dikes and sills, and this is what's known as the Assynt Alkali complex. There's a whole series of dikes and sills which on a diagrammed quartz, plagioclase, alkali feldspar, feldspathoids. We're looking at the alkali end member here, which is dominated by potassium feldspar. So granites, granodiorites are over in this region, quartz, plagioclase, potassium feldspar, and the cyanites and the lamprifiers that we're looking at in Assynt are in this end member spectrum here. So they're feldspathoid bearing alkali igneous intrusive rocks. Okay, so here we've got a rock that is completely different from all the sedimentary rocks that we've seen today. This is an igneous rock. It clearly has an igneous texture. You can see little tiny needles of black hornblende and tiny little green pyroxenes in this rock. So this is an intrusive igneous rock that has been intruded into the Igneous limestone. This is one of the sills that we call the lampriferic series sills, and lamprifiers are a group of basaltic mantle-derived rocks that are intruding in an intraplate off-axis tectonic setting. This alkaline intrusion, this lampriferic sill, has been placed into the Igneous limestone group, and the upper contact of this sill, which is maybe 2 or 3 meters wide, is right here, and you can actually see a baked margin along the contacts between the limestone or dolomite and the lamprifier and the igneous rock. So this was intruded at very high temperatures into a limestone that was cold, and it baked the margin, cooked the margin up to form this chilled margin that we see right here. This is just one example of tens or hundreds even of these alkali igneous intrusions that intrudes through the Cambrian Ordovician section in the Moine thrust zone. Along the foreland we've seen the Canis porphyry, which intrudes through the undisturbed foreland, but in the Moine thrust zone we have a whole series of these alkali igneous sills that we can use for establishing the criteria of were they intruded before or during or after the thrusting. And because most of these lamprifiers are affected by within the Moine thrust zone, within the Searle thrust and the Benmore thrust, these must have been intruded prior to the thrusting. And we know that these rocks are all about 430 million years old. So this is the British Geological Survey map of the Assynt window. And the window is this is the Moine thrust that bulges up into this culmination. It shows all the components of the Caledonian orogenic front that we're looking at here in northwest Scotland. So in the west we have the stable foreland comprising the Lewisian basement gneiss in red, which is the 2.7 billion year old granulite and fibrillite facies gneisses. They are intruded by a series of these dikes, which are all oriented in a northwest-southeast orientation, both ultramafic dikes and dominantly mafic dikes. These are called the Scourie dikes, and they were intruded at 2.4 billion years old during a regional extensional event. The whole Lewisian granulite and the Scourie dikes was then metamorphosed during the Laxfordian orogeny about 1.7 billion years ago, when the granulites were retrogressed to amphibolites, and the whole of this region here underwent its last thermal event. The Lewisian basement gneisses are unconformably overlain by the Torridonian Sandstone, this orangey colour rock here. The same rocks that we saw in Loch Assynt. Here's Loch Assynt. This is the Torridonian sitting on top unconformably of the Lewisian basement. Both Lewisian and Torridonian are unconformably overlain by the Cambrian Quartzites in grey. And the double unconformity that we saw at Loch Assynt is right there. So we were walking a section along the north shore of Loch Assynt, from basement gneisses through Torridonian to Cambrian up to the Durness limestone, which is Ordovician. And the Searle thrust is the youngest, lowest thrust sheet of the Moine thrust zone, is this unit here. And you can see above that, there's all sorts of structural complications. Loads and loads of imbricate thrusts that are repeating the sequence. So here we have a repetition of the Cambrian and the Ordovician sedimentary sequence above the Searle thrust. Now there's 2 or 3 intermediate thrusts within the Moine thrust zone, which bring up slices of Lewisian basement above the Cambrian Ordovician sediment. Clearly that is putting older rocks onto younger rocks. We're standing here at Loch Glencoul, and we are overlooking what's known as the Glencoul thrust, which is this prominent band that you can see in the far distance there. And that band is putting Lewisian gneisses up in the skyline structurally over the Cambrian Ordovician sedimentary sequence below. So that's clearly putting older rocks over younger rocks, and the thrust is dipping to the east and verging to the west. So the whole of the Moine thrust zone shows a series of thrusts that are emplacing these lochthonous rocks of the Moine sequence over the stable Laurentian foreland of Western Scotland. Now, a number of factors to look at here is within the complications of the Moine thrust zone, all these imbricate thrusts repeat the Cambrian Quartzites and all the sedimentary sequence up to the Durness limestones in blue. These rocks here are intruded by a whole series of alkali sills in purple, which we'll come to later when we see the Borrolon complex down here. There's 2 major alkali syenite igneous intrusions that are truncated by thrusts above and below. This is the Loch Ailsh syenite,
This is the Borrolin syenite, and we're going to look at those tomorrow. In the Moine thrust zone, this zone of complication between the Searle thrust at the base and the Moine thrust at the top, you can see that there's all sorts of structural complexities. In the Searle thrust sheet, there's numerous repetitions of the Cambrian Ordovician sedimentary sequence. A major feature here is another thrust, the Benmore thrust and the Glencoul thrust, which in place thrust sheets of basement, Lewisian basement, over Cambrian Ordovician sedimentary cover. Clearly these are putting older rocks over younger. The thrusts are all dipping to the east and verging to the west, transport direction to the west. So we have a series of alkaline intrusions, including the Canis porphyry, which intrudes the Fallen sequence, and two major alkaline intrusions in the southern part of the Assynt window. This is the Loch Ailsh intrusion, which is truncated by the Moine thrust above, and it's carried on the Benmore thrust below. This is the Borrolin syenite intrusion, which we will see in the next few days, truncated by the Benmore thrust above and carried on thrust below, the Borrolin thrust below. So we can use the timing of these alkaline igneous intrusions to date the timing of deformation, because we know that these were intruded prior to being carried on the thrust sheet. And the ages of all of these are between 430 and 431 million years old. And that is as good a timing constraint as we can have on the initiation of the Moine thrust. So the Moine thrust itself carries the Moine schists, all this yellow material here, over the imbrications of the Moine thrust zone over the stable foreland. And the Moine schists are a series, kilometres thick, of unfossiliferous Proterozoic metamorphic rocks. And this is the zone which is a major intracontinental thrust fault. The hinterland of this Moine thrust is all metamorphic rocks, so they're the eroded remnants of a deep Himalayan-type mountain belt. 430 million years ago, the hinterland of the Moine thrust was probably looking similar to the Himalayas today, and it's had hundreds of millions of years of erosion to get it into the state that we see it today. Okay, so we've now walked through the stratigraphy of the whole of the foreland section, from the Lewisian basement through the Torridonian, through the Cambrian basal quartzite, pipe rock, Fucoid bed, grit, Igneous limestone, up to the Searle thrust, which is the basal thrust of the Moine thrust zone. We're now sitting right above the Searle thrust, and the strike of the rocks goes through all sorts of contortions with folds and thrusts. So before we start mapping the structure, a basic recap on how to take strikes and dips. So this is a bedding plane. This is part of the Igneous limestone, and we know it's a bedding plane because of compositional difference as you go up strike. So given the irregular nature of this bedding plane, you can either take a strike and dip direct, or you can use any board, your notebook or field mapping slip, for example. So to take a strike, the strike is the horizontal intersecting with the bedding plane. So you need to get your compass clino in the horizontal position, and then you move the bezel around until it fits the north and the south arrow, and you read off the strike here. And that strike is 145 degrees, so northwest, southeast. The next thing is the dip. So you move the bezel around to 90 degrees, and the readings are all here. So we turn the compass clinometer, and you move it so that the arrow is free hanging. It's very important. If you tilt the clinometer, the arrow gets stuck. So you move the clinometer around to the direction of maximum dip, and that dip direction is going to be orthogonal, 90 degrees to the strike. And then you get your eye along here and you read off the dip, and in this case it is about 64 degrees. So if you have a strike direction and a dip, you must also put the direction of dip, because it could be dipping that way or it could be dipping that way. So in this case, the dip direction is orthogonal to the strike, and it is towards the southwest. So the reading on the map would be 145 degrees strike, 62 degrees towards the southwest. There's another way of doing it. If the surface of the bed is so irregular, you can use any flat surface, a notebook or a mapping board. Be careful with mapping boards, so never take a strike direction, because sometimes the magnetic inclination is altered. So in this case, we're looking at the direction of maximum dip. So previously we'd taken strike, dip, and direction. This alternative method is simpler. It is simply the angle of dip. So I move this to 90 degrees and read off the angle of dip, moving this around so the arrow is free falling and the angle of dip is the wrong way round. So anybody can make mistakes, and the angle of dip, as we read before, is approximately 64 degrees. Now we want to get the azimuth, the direction of dip. So this is 64 degrees towards an orthogonal direction to the strike. Two very, very simple readings, the dip and the azimuth, the direction of dip. That's all you need to take. And then you put that on your line on your map and carry on. And you should be taking 100 strike and dips a day as you traverse across the terrain like this. A strike and dip should be taken on any planar feature. Bedding plane when it comes to sedimentary rocks, or a schistosity plane when it comes to metamorphic rocks. You can take a strike and dip on a fault, on a joint, or any planar structure. Lineations along fold axes are lines, so that is the plunge of the lineation and the direction of the lineation. All of this is in the PowerPoint video 1, which you should have got back in Oxford prior to this field trip. All the structural observations and how to take the readings are in that PowerPoint, so make sure you look at that.